This is section 1.3, Evaluating Limits Analytically. So last section, when we did limits graphically and numerically, those were actually guesses. Those numbers looked like they were getting closer and closer to, say, 3. On one side we got 2.99997, and maybe on the other side we got 3.00002 or something. So we thought it was pretty close to 3. And now we're going to find out how to do that analytically. That is, for sure we'll know what the limit is. Now, one thing I have to stress, and I think I said this last time as well, is if you have a limit for a function that has a removable discontinuity, for example. So as you get closer and closer to the x-coordinate that produces that discontinuity, you're getting closer and closer on the left to y equals L, and from the right you're getting closer and closer to L. And so we would say that the limit as x approaches c for this function, which I'll call f of x, is L, because from both sides we're approaching the y value of L as x gets closer and closer to c from the left and from the right. So that's one of the situations where we have a limit. But notice that in this particular example, f of c has no value. That value doesn't exist. And so it doesn't matter what f of c is, it's what f of x is approaching as a y value as x gets closer and closer to c. It has nothing to do with what, at least not necessarily, have anything to do with what the actual y value when x is c, whatever that is. Now, there are some problems, like if I then came back and said, okay, I want to do this one as x approaches d. There's no missing point, there's just a y value there. And let's say that this approaches some number m. Then for this one we could say that the limit as x approaches d for f of x, from both sides it's approaching m, okay? But this time f of c happens to also be equal to m. And that's a nice circumstance because the limit value and the function output value happen to be the same. So when we can substitute c into the function for x and get the limit, in other words, when this happens, that the limit as x approaches d of f of, oops, I wrote a c there, of f of x is actually equal to f of d, then we can actually evaluate the limit analytically by doing that direct substitution. And there are certain classes of functions for which you can do that. So not for every function, but for some functions at least, you can evaluate the limit analytically simply by substituting in to the function with the number that x is approaching. Okay? So let's look at Theorem 1.1. If b and c are real numbers and n is a positive integer, then number 1, the limit as x approaches c of the constant b is b. So let me show you what I'm talking about. What we're talking about here is a function that is constant, like y equals 4. This function has a constant output of 4, no matter what x is. The y value is 4. And so if you put any number c into that function, for every x, there is no x, you'll get 4. You'll get that same value back. Okay, number 2. The limit as x approaches c of the function x is c. And that's a direct substitution. So add this to the list of things for which you can substitute and get the right answer. So y equals x is the function. And if you come up with a value of c here, the coordinate of that point is c, c. That's like 1, 1, 2, 2, 3, 3, 5, 5, 20, 20, -1, -1. Those are points on the graph y equals x. And so the x and y coordinate are always the same. Of course, that's what the equation tells us. And so the limit, as you approach c from below and from above, it's still approaching the y value of c. And this one too, let me go back to it. As you approach c from the right side and c from the left side, your y value is approaching 4. Okay? And then number 3, the limit as x approaches c of x to the nth, where it's any power, that will be c to the nth, meaning you can just simply substitute. For each x, replace it with a c. All right, so that means that there are several of these types of problems that we can do. Let's do example 1, part A. It asks us to find the limit as x approaches 2 for the constant 3. And as we said above, the limit of a constant is that constant. That may be something you want to kind of memorize as a saying. The limit of a constant is that constant. Okay? And if we find the limit as x approaches -4 of x by substitution, put -4 in for x, and we get the answer. And C, the limit as x approaches 2 for the function x squared, we can just simply substitute in 2 for x and simplify. All right. So now here are some other properties of limits that you need to know. And this is Theorem 1.2. If b and c are real numbers and n is a positive integer, and f and g are functions that have the limits, the limit as x approaches c for f of x is L, and another function as we approach the same value for x approaching c for g of x, let's just say that that answer is known to be k. And so the first one of these, called the scalar multiple, says that if we have a limit as x approaches c of some constant b times f of x, as long as we can, if f of x is one of those functions that we can find by substitution, we could substitute that in, but our answer would be b times that limit as x approaches c of f of x. So in other words, that constant b can be brought out in front of the limit. And then, of course, we're told above that that limit is equal to L, so this is b times L. Okay, so that's one of the properties of limits, is a scalar, constant multiplier can be brought out in front of the limit. Okay, the sum or difference property. If we have the limit as x approaches c of f of x plus g of x, or by the same token, f of x minus g of x, either one, then we can find that limit by taking first the limit of the first function and then adding or subtracting the limit of the second function, and using what we are given up above by substitution, we know the limit for f of x is L, plus or minus the limit for g of x is k. Number 3, the product of two functions. Okay, the limit of a product of f of x multiplied by g of x, we can take the limit of the first function and multiply it by the limit of the second function, and then by substitution the first limit is L times the second limit is k, so it'll be L times k. Okay, quotient. And as you know, with quotients you have to be careful because we can't divide by 0. So anytime I have a rule that involves a quotient, I'll probably need to add something about, oh, and you can't divide by 0. You'll see that quite often. So if we have a quotient of two functions whose limit we're trying to find, you can take that limit and separately find the limit of the numerator and divide it by the limit of the denominator, and by substitution that will be L over k. But of course we can't divide by 0, so I need to say, oh, and k can't be 0. Okay. So you might see that the limit is kind of like something that you can distribute to the functions individually inside of addition, multiplication, division, and just take a limit of each individual inside thing. So if that helps you understand it, that's good. And then the power rule, if you have the limit as x approaches c of some function that's been raised to an n power, then you can take that limit inside and evaluate the limit of that function inside, get that answer, and raise that answer to the nth. And of course that limit for f of x we said before was known to be L, so that would be L raised to the nth power. Okay, so these are very important properties, and you'll hear me talk about them many times, including even in Calculus 2. I'll refer to these to a certain extent at different times. So these are important properties of limits. The first three up here, limit of a constant is that constant, limit of x is c, and the limit of a power of x is c to that power, and then these 5. Okay, so here's an example, and in this particular example I'm going to slow myself way down, and I want you to know that on the test I will also expect you on a problem like this at least once. I'm going to say evaluate this limit showing all properties of limits being employed that are used, or something to that effect. And I'll say do this one step at a time. This will take lots of steps. So here we go. Because I see the addition there, I'm going to split that according to number 2. And by the way, you don't have to memorize these by number. I'm just referring to the property I'm using so that you know. the limit of the first thing plus the limit of the second thing. So I've only used one property in this step, the number 2. Then for this first term, that constant 4 that's multiplied by x squared, that scalar, can be brought out in front. And I'm trying to do only one thing at a time, so I'm not changing this one yet. Okay, then x squared is a power of x, and so that can be accomplished by substitution of 2 in for x. And then finally, the limit of a constant. I've also done some arithmetic. The limit of a constant is that constant, and then arithmetic takes us to our final answer of 19. Okay, we've only done one thing at a time, and so this shows that you understand the properties of limits, because you can break it down into individual steps, and there will be a test question where you're required to do just that. If you look at a graph of this function, as x gets closer and closer to 2, the y value gets closer and closer to 19, and so that does make sense. Now, if I have any polynomial function, like 4x squared plus 3 is a polynomial function, every time there's addition or subtraction, I'll split that up into 2 limits. And then for every scalar like 4, I can bring that out in front. Then I'll have powers of x for which I can substitute, maybe even a plain x for which I can substitute, and then the limit of a constant is that constant. And so if it's a polynomial function like this one, because those types of things are the usage of those properties of limits, as we just showed, we could actually have done this problem by substitution. Because if I substituted 2 into that polynomial, I would have gotten 4 times 2 squared plus 3, which is, of course, what we did up above to get the answer of 19. So I'm promising you that for every polynomial function, direct substitution is valid for all polynomial functions. Also, rational functions, which are defined to be the quotient of 2 polynomials, p of x over q of x, where p and q are both polynomials. Well, if I'm asked to find the limit as x approaches c for f of x, by substitution, that's the limit as x approaches c of p of x over q of x. Then using property number 4, notice I had to look because I don't have it memorized by number either. Property 4, that will be the limit. Oops, pen stopped working for a second. There we go. The limit of the numerator function divided by the limit of the denominator function. And because those are both polynomials, according to what I just said a moment ago, for every polynomial function, you can evaluate the limit as x approaches c using substitution. So this should be p of c over q of c. Whoops, I wrote x, my bad. Q of c, which of course is what f of c would have been, provided that Q of C is not 0. As long as Q of C isn't 0, then we can find the limit of any rational function by substitution. As long as we don't divide by 0, we're in good shape. So that's a pretty big list of functions. Think of all the polynomials and then all the rational functions you can form as a quotient of two polynomials. That's a lot. Okay, so that's actually Theorem 1.3 in a nutshell. All right, so let's do an example. So I can do that here in this empty space. The limit as x approaches 1 of the function x squared plus x plus 2 divided by x plus 1. And because that's a rational function, according to what we just learned, we can try substitution, and if substitution leads us to anything that has division by 0, we're going to have to back off and do something else. But if substitution leads us to division by anything besides 0, we're in good shape and we have evaluated the limit. So I'm going to try substitution by putting 1 in for each x in the problem. I'm not getting division by 0, so we're in good shape. So this is 4 over 2, which is 2. Okay, kind of nice to know that about certain types of function, that substitution gives you the right answer, and you always want to try that. And so if you look at the graph of this function, you'll see that as x approaches 1 from the left and right side, the y value is getting closer and closer to 2. All right. So polynomials and rational functions are two of the three basic types of algebraic functions. The third type, those that involve a radical, are also algebraic, are now to be dealt with in Theorem 1.4. If you have the limit as x approaches c of the nth root, so there's your radical, of x, sometimes you'll be able to substitute and get an answer, sometimes you won't. So I'm going to show the substitution answer first. Now, let's think about this. If I had like the square root of 16, does that have an actual real number answer? Oh, of course, it does, 4. And what about the square root of negative 16? Does that have a real number answer? No, that's not a real value. You may actually know the imaginary answer that's correct, and that's wonderful. But we're looking for real number answers because graphically we're looking for a real number y that the graph is approaching as x gets closer and closer to something. So that would not be okay. So what's the cube root of positive 8? Is that okay? Yeah, it's 2. And what's the cube root of negative 8? Does such a thing exist? Is that a real number? Is there a real number that multiplied by itself and then multiplied by itself again you get negative 8? Yeah, that's negative 2. So the lesson for this to take forward is that you can simply do substitution if n is odd, like cube root, 5th root, 7th root. You can just substitute. However, when n is even, sometimes you can and sometimes you can't. If n is even, c has to be non-negative. Like 16, the square root of 16 exists, so we take it, it's good. So there's that little important thing to make note of, is that if n is odd, you can take the cube root or 5th root of any real number, negative, positive, whatever. But if it's an even, like square root or 4th root or 18th root, you can only get a real answer if you're taking, say, the 18th root of a positive number, not if it's negative. You'll get a non-real answer in that case. So now let's talk about the composition of functions. Let me remind you of what that is. If f of x is defined to be x squared minus 3x, just making up something here, and let's say g of x is 4 minus 2x, then f of g of x is the composition of f and g, and by substitution that's going to be f of 4 minus 2x, which means we're substituting into the f function for each x with 4 minus 2x. So it'll be 4 minus 2x squared minus 3 times 4 minus 2x, which we then simplify. So let me do that really fast. This will be 16 minus 16x plus 4x squared, doing the squaring. And then distributing, that'll be minus 12 plus 6x. And so our final answer would be 4x squared minus 10x plus 4. That's a composition. So if we have a composition like that and we're trying to find a limit as x approaches c of that composition, I just talked about this the other day in calculus 2, so this is something that's very important. What you can do with that is you can go inside to the innermost function and evaluate the limit as x approaches c for g of x. And if that limit is known to be L, the limit of g of x is L, then this will be f of that limit answer, which means you'll take your answer for the limit inside and put that answer in as an input for the f function. Okay, so we should probably do an example of that so that you are not confused. This is not that hard to do, but it is a proper rule that you will need to know how to deal with. The idea is basically if you can substitute, you substitute. That's the short of it. If you can substitute, not have something where you're dividing by 0 or getting the square root of a negative or something like that, then you're good. Okay, this is the square root of a function. So the outer function is f of x is the square root of. The g of x is the polynomial under that radical. So I'm going to go inside with my limit to the innermost function and take the limit as x approaches 0 of x squared plus 4. Since that is a polynomial, I can do that by substitution. So by substitution, that's 0 squared plus 4. We'll get an answer of 4. And then do the outer function of that. The square root of our answer 4 is 2. Okay? B. The limit as x approaches 3 of the cube root of 2x squared minus 10. All right, so the outer function is cube root of, so I'm going to leave that to be done later and go inside and take the limit of the polynomial function that's under that radical. Okay. And since that function under the radical is a polynomial, that can be evaluated by substitution. Let's see, 3 squared is 9, 2 times 9 is 18, 18 minus 10 is 8, and the cube root of 8 is 2. Okay. So we've seen lots of functions whose limits can be obtained simply by doing direct substitution. Many of the algebraic functions can be evaluated that way. The only caveat is if you're trying to divide by 0, that will not work by substitution, and you have to back off and do something different. The 6 basic trigonometric functions also exhibit this desirable quality of being able to evaluate them using substitution. And so if you look at Theorem 1.6, I'm not going to write all these down, but every single one of those limits of a trig function can be evaluated by substitution as long as you use a number that's in the domain of the function. For example, you can't take the tangent of pi over 2. It's undefined. So if you try to do the limit as x approaches pi over 2 of tangent x, let me write that down. That one actually doesn't exist. Because you can't substitute pi over 2 for tangent, because remember, tangent of x is sine of x over cosine of x. And sine of pi over 2 is 1. Cosine of pi over 2 is 0. 1 divided by 0. Not a number. So that limit doesn't exist. Okay? But as long as you're in the domain of the function, you could do substitution as long as it doesn't give you division by 0. Again, that's the big idea. If you get division by 0, you have to do something else. All right, so let's do a few examples. The limit as x approaches 0 for tangent of x. Well, as long as 0 is in the domain of tangent, we're good. Tangent of 0 is what we'll get. And the tangent of 0, sine of 0 is 0 over cosine of 0 is 1. 0 over 1 is 0. We got an answer, and we're good to go. B, the limit of, as x approaches pi, of x cosine x. So notice this is a product of two functions. So we're going back and reusing some things we learned earlier. The limit of a product of functions is the limit of each factor, the limit of x, multiplied by the limit of the other factors. There's only one more, so times the limit as x approaches pi of cosine x. Of course, since x is a polynomial, we just substitute and we get pi. And we'll try to substitute in for cosine, into cosine with pi, cosine pi. And as long as that's a good number, we're good to go. And the cosine of pi, of course, is -1. Pi times -1 is the opposite of pi. And yes, you do need to know trig values for all kinds of angles. So please don't forget that that's something you're supposed to know how to do. You might need to go back and review it. So anything that we do here that you say, oh no, I haven't thought about that in a while, that means you probably need to go back and review it and make sure that you can do the, say, trig here. Okay, so this is a composition, and so this is something squared. So we're going to go inside and take the limit of the function that's being squared, sine of x, as x approaches 0, and then we'll square that result. This is using one of those properties from earlier as well. So the limit of that, if it exists, will be found by substitution. The sine of 0 is 0, and then 0 squared is 0. Okay, so I've run out of room on this particular recording, so I'm going to move to another one. So this ends part 1.